Hello, my name is Santiago Avila. I'm a researcher at CIEMAT, a national lab in Spain. And today I'm going to talk about BAU measurements from DES and its impact on dark energy. So dark energy was designed, the dark energy survey was designed with four main goals, basically to constrain the nature of dark energy with four different probes: type 1 supernova, Baryonic Acoustic Oscillations, weak lensing, and cluster counts. It has hundreds of scientists around the world in these countries and institutions that you see over here. And it actually consisted on two surveys, one wide survey covering this southern sky of 5,000 square degrees over 6 years, and a type 1a supernova with 10 small fields repeated with repeated observations every 5 years for 5 seasons. So BAU can be used as standard ruler. As you all know, this sounds was propagated in the early universe up to the epoch of recombination, then remodeler over densities at a given center, propagate to this sound horizon over here, which you can compute from first principles, and then you can count an excess of galaxy pairs separated by this particular distance that then you can use as standard ruler. This standard ruler give us relation of the angular distance to redshift relation, which in turn depends on the cosmology, the quantity of matter, curvature, dark energy and type of dark energy. So the DES-Y6 analysis, the final analysis, set up a small team, but hardly working on this, and many other people contributing in different ways. There's different aspects of this massive effort. I was coordinating this as a large-scale structural science working with co-convener, and we optimized the BAU sample selection with 16 million red and bright galaxies in these other people led by Juan. Eventually, we got 6 tomographic pins between redshift 0.6 and 1.2. We used 3 different redshift estimators to make sure that our measurements are robust, 3 different clustering statistics, and test over 2,000 simulations. We did all the analysis blended and a lot of checks to verify that our measurements are robust. In the end, all the measurements are isolated in this alpha, which tell us basically how much we need to move our peak position of the BAO from a template in a given cosmology to the measurements. And this shifts and codes all the cosmology in this angular distance at a given redshift and the BAO scale, the sound horizon. These are the measurements of clustering, angular correction function with these points with error bars, which come from theoretical covariances. We have 6 tomography pins. The largest pin, highest redshift is over here, lowest redshift over here. Both the geometry of the standard ruler and also expansion of the universe point to the direction that the ones at higher redshift will look smaller on the sky. So these lines are the best fit, trying to fit at the same time all the peaks together. We're not trying to fit one peak individually in this analysis, but we have one single alpha that contains all the cosmological information and an effective redshift that covers all this 0.6 to 1.2 redshift. So this is what the angular power spectrum looks like. We also do analysis on this space, and here peak becomes some wiggles. And we also use the projective correction function where we use the comoving transverse distance as a separation. And in this case, all the peaks align together, and you will see later that because of this property, we can put all the signal together of all these 6 pins and then get a larger signal to noise on this. But our previous analysis uses all these 6 redshift pins, and all these 3 clustering statistics give very consistent results. You put everything together in one single correction function, then you see by eye already this peak of the BAO, and you see also by eye this deviation from Planck template. This is a 4% deviation. As you can see here, we are 96 more or less, and 1 would be the Planck-LCDM reference, which is the assumed cosmology when in the template. And we checked that our measurement is very robust. We added some systematic error, but are mostly dominated by statistics. And we tried different clustering estimators that I already described. Different analysis variations, changing the way we compute the covariance, the scale cuts, or scale binning, the reference cosmology, or the data calibration with nulling the systematic weights or changing the N of C calibration, the redshift calibrations, and all of them get very consistent results. Eventually, we get this measurement. As you see, it's 2 sigma away from the reference Planck-LCDM. It improved a lot the constraints with respect to year one, and it's the most constraining measurement in this redshift range at the moment of publication, which is basically we compare to stage 3, so BOS and EBOS. So yeah, with this, we're measuring at effective redshift of 0.85 with this 2.1% precision. So this, we are around 2 sigma below Planck. The most precise measurement from a photometric survey, and it's competitive, as you can see here, with some spectroscopic surveys designed to measure BAO. We're competitive in this particular redshift range. And of course, we only showing angular BAOs, but some of these surveys will also allow to measure radial BAO, which we cannot do with photometric surveys. But yeah, at this moment of publication, we were the most precise angular BAO at this redshift, below this 0.75. Okay, but a few months after our measurements, first stage 4 experiment released their BAO measurements. This is DESI DR1, and we see that some of these measurements are much more smaller now, but we will still get competitive results in the redshift range, like comparable error bars to this LRG2 point, and similar level of deviation from Planck-LCDM. So this is interesting. Okay, so I already talked about BAO. Remember that we have all these probes within DES, but these 2 probes are the ones that probe only the expansion history, whereas the weak lens in the clusters will also probe the growth. We'll have different talks of DES people, Brody and Supernovae and David and Octavio about 3x2. But yeah, I will be focusing on the combination of BAO with Supernovae because these are the 2 that are sensitive to only the expansion history, and they were also the ones that were done earlier in our analysis. So actually, yeah, the DES Supernova team put together this Hubble diagram, which is impressive work with 1600 photometrically classified supernova, which follow out the spectra from OSDES. I'm not going to go into the details. You can see the other talk as I mentioned, but basically they released in 2024 this 2 sigma deviation from lambda CDM in the wCDM space only from DES supernova. This is impressive. And if you combine with other data sets, you could see that this is well beyond this 2 sigma deviation. In February, we also released this 2 sigma BAO measurement, 2% measurement, which is 2 sigma away from Planck. And in April that year, DESI released the DR1 analysis with very impressive measurements that combined with our supernova and CMB give a 3.9 sigma preference for WA. So it was a very interesting year for the dark energy and lambda. So with this context, we set out a team to check what is the combination of DES supernova and DES BAO going to tell us about expansion history. So in this analysis that was released 1 year ago, we will refer to BAO as our BAO, DES, just DES-Y6, and supernova just DES supernova. And then we will be combining with things like CMB, only using temperature and polarization power spectra, so no lensing. Or in some cases, we can just restrict ourselves to background quantities and then use just a theta star, which is just the BAO scale on the CMB. You can also help yourself with BABN to avoid to calibrate your BAO without the CMB, let's say. And this is the reference over here. If you combine these data sets, just the background ones, you find supernova is very constraining and lambda CDM in omega matter, whereas BAO with 1 single point, you need to calibrate it very well with BBN and theta star to obtain competitive results. And then you find a low value of omega matter. You can see these measurements are in tension. If you try different combinations in triplets of all these 4 measurements, you see that measurements move a lot around. So you could say that it's hard to reconcile all these measurements in lambda CDM. This is the main conclusion we draw here. So we will go to other spaces. But if you try to combine them, mathematically you can do it. Then you go to this purple contour, which is very compatible with CMB contour. So this is interesting. And if you zoom into this and you add to CMB BAO, you will see that it's pushing to the left, so lower omega matter, whereas supernova is pushing to the right, higher omega matter. This is a trend that we will be always finding in this paper. Okay, so let's go to other models and see if the tensions are released. Actually, we see it doesn't, no? Like this contour BAO, supernova BB, and theta star are very incompatible with BAO, supernova, CMB. So the tension doesn't really release, maybe even increases. So kLCDM is not the solution. We could try to wCDM, just one single parameter for the equation of state of dark energy. And in this case, we still see that the tensions are still persistent. No, it's around 2.5 sigma tension between the supernova alone or the combination of CMB plus BAO. Also, since BAO and supernova are pushing in different directions and they have different effective redshift, this could be already a hint for evolving dark energy. We find that when we go to W0WA, all data sets are together are compatible, and if we take the most constrained one, BAO supernova plus CMB, they lie here, so it's around 3 sigma away from the lambda CDM point. If we only use the background probes, including BBN and theta star, then we are around, still also around 3 sigma. Similar deviations are found if we switch our BAO point with DES's point, DR1, so we get 3.2 sigma, they get, with their points, we get 3.6 sigma. This is interesting that with one single point from our BAO, we get similar tension as their 7 points. This does not go in the direction of solving the Hubble tension, so our measurement in W0WA with all our BAO plus CMB is still on the low side of H0, so it's not solving the tension. We also get measurements from the cosmographic expansion, so not assuming a physical model, but just stellar expansion of the expansion history. And in this case, yeah, we also get a low value of H0. Since our paper, there's last year, there's been updates mainly on the Dovecki supernova with a new calibration that changes a bit of the Hubble diagram. You can see the details in this paper on Broadstock, also in this conference. In this case, our tension goes from somewhere around 3 sigma to somewhere around 2.5 sigma. So it's slightly released with this new Hubble diagram. So this is also interesting. And this was reported in this paper led by Juan Mena that I also coordinated. The other thing we wanted to test is, okay, so we said our BAO gives 3.2 sigma. If we switch to DESI DR1, it's 3.6. We could combine them together, but if we ignore the covariance, they overlap in area, so they have some covariance that we cannot estimate very well. So if you ignore that, this is 4.2 sigma. This is very interesting. Okay, but yeah, has the caveat that we are ignoring and maybe repeating information, right? So also in this other paper that I just mentioned, we also studied this. So we did say, okay, let's try to remove this area of overlap. It's not a small area, and then see what happens. What happens is the first that error bars get a lot bigger. So we go from here to here. It's a lot bigger, and also, well, slightly bigger, and also the central value shift. So we are only now 1 sigma away from Planck. And also, by the time of this paper, we already had in hand the DR2 data, so we added that. And in this case, DR2 data was already very constraining. Error bars now are a lot smaller. So in this case, our measurement, which is only 1 sigma away from Planck-LCDM, it's only adding 0.1 sigma to this tension, okay? But yeah, we wanted to test whether this was still adding something. The good thing is at this point, it will also be used now for combination with 3 times 2 point when we also want to use DESI data. So, and W0WA, so, you know, we have this measurement that can be combined with DESI safely without any covariance. Okay, when we put everything together, our BAO, their BAO, excluding the area of overlap and CMB and supernova, then we get 4.1 sigma tension with LCDM, but if we move to the supernova from Dovecki, then the tension decreases to 3.1 sigma. So this is kind of the current status, right? But still, what was interesting is that our BAO measurement could give us an independent measurement from DESI BAO, and we still get 2.5 to 3 sigma deviation from LCDM. Of course, with more data, we'll see what happens. And now, soon we will have all the combinations of clusters and weak lensing. Some of this is already done, like 3x 2-point analysis is already done. So you will see talks by this from David and Otavio. Okay, so in conclusions, DES-BAO is the tightest constraint from a photometric survey on the angular BAO. It's competitive with spectroscopic surveys, although those also give us some radial measurements. It's 2 sigma or 4% below Planck CMB prediction. So when we combine our BAO with Supernovae from DES, they actually push in different directions in the parameter space. One prefers high omega matter, the other one prefers low omega matter. So this results in several 2 to 3 sigma tensions in λCDM or extensions like kLCDM or wCDM. Only when we go to W0, wCDM, in dark energy, then all data become consistent in this space. And then this combination gives a 3 sigma deviation from λCDM. It's also consistent with expansion history only probes that we mark over here. So now with the update of DES-Dovicki, this tension reduces by around 0.5. So we are 2.5 sigma. And but we will have the final W0WA constraint from DES coming soon. Still, you can see the talk by Otavio or the paper that will be coming out soon. Also, we're still waiting for the cluster. So, this is not the final word from DES. This is very interesting, the tensions that we're finding. So stay tuned for new data. Thank you.